Okay, today we are going to study the last two tests that we're going to learn for proving whether a series converges or diverges. And both of them are quite simple. The first one we're going to look at is called the ratio test. And the ratio test basically says that if you take the ratio of the n plus 1 term divided by the a sub n term, if that ratio is less than 1, then the series converges. If that ratio is greater than 1, then that series diverges. And if that ratio is equal to 1, then the ratio test is inconclusive. You can't find anything out about the series. You got to use a different test. So let's see if this just makes a little bit of logical sense to you. Let's say, for sake of argument, we find the millionth term. And let's say that term value is, let's say, make it easy, say it's 2. And then we find the million and first term, and let's say that that is 1. Okay, so you have the millionth term is 2. The very next term after that is 1. Well, if you divide the n plus 1 term, or here's the n plus 1 term, is the term that's the last one, divided by the one that came before it, 2, well, that's less than 1, and that means it's going to converge. You say, well, how do you deduce that? Well, let's think about it. If you go all the way out to the millionth term, and then the million and 1 term, and the numbers are still going down, and which means that if they're going down, that means when you divide the next number by the previous number, you should get a number less than 1. Then that's telling you that the numbers are going down, it's decreasing, it is going to converge. All right, and the converse is true here if it diverges. Now, the important thing about this test is not necessarily understanding all of this, but when to know when you should use the ratio test. The ratio test is best used when you have a series that involves exponentials or factorials. So if you have a simple series that involves exponential functions or factorials, this test is a good, simple, and easy test to use. Okay, we have our first example here, and it says determine whether the following converge or diverge. And so we have the summation from n equals 1 to infinity of 2 to the n over n factorial. So once again, we have a situation here where we have on the top, we have an exponential function, and on the bottom, we have a factorial. So as our little hint told us, when we have series that are involving exponentials and factorials, it is often a clue that we could use the ratio test. So, ratio test says that we need to find the a to the n plus 1, a n plus 1 term. So that means every place where we see an n, we're going to replace it with n plus 1. So a of n plus 1 is equal to 2 to the n plus 1 over n plus 1 factorial. And then a sub n is simply the function that they gave, the series that they gave us. And now we're going to divide those two. So we'll come over here and we will put the a n plus 1 series on the top. So 2 to the n plus 1 over n plus 1 factorial, all divided by 2 to the n over n factorial. Now, this is the only time you'll see me do this, because dividing by a fraction is the same as multiplying by the reciprocal. So from now on, this is how you'll see me write it, times the flip of that. So it'll be n factorial over 2 to the n. Now we got to get a little clever here to rewrite this. We have to remember a property from Algebra 1, that when you have 2 to the n plus 1, we can break that up into 2 to the n times 2 to the first, because when you have like bases, you add the exponents together. So that's going to give us that. And if we multiply by the rest of the numerator, you get n factorial. And then on the bottom, we have this 2 to the n. So I'm going to put that over here. Now we've got n plus 1 factorial. Now we need to do something clever with that. And for that, I'm going to use basic numbers to explain that. Let's say we have 5 factorial. And that is equal to 5 times 4 times 3 times 2 times 1. But let's say you don't feel like writing all the numbers out. You can write that as 5 times 4 factorial, because 4 times 3 times 2 times 1 is 4 factorial. So we can replace all of that with this. So how do you write a factorial? You write a factorial as the number times 1 that came before it, factorial. So going back to our problem, we have an n plus 1 factorial. Well, that's just going to be n plus 1, the original number, times the number that comes before n plus 1, which means we'd have to subtract 1 from n plus 1, which you get n factorial. And now we see some things that are going to cancel. We have 2 to the n that cancels. We have n factorial that cancels. And that leaves us with the limit as n approaches infinity of 2 to the first, which is 2 over n plus 1. Well, as n approaches infinity, this limit equals 0, and that is less than 1. So, therefore, this series converges by the ratio test. All right, in this next example, we have, once again, a series here, n squared, 3 to the n plus 1 over 2 to the n from 1 to infinity. And so we see that there are some exponential functions involved here. So we're going to just use the ratio test. And so our a of n plus 1 means every place we see an n, we're going to replace it with n plus 1. So that's going to result in n plus 1 squared. And you got to be careful with all this stuff. And so that's going to be times 3. And we're going to replace this n right here with n plus 1, which is going to make it n plus 2. Over, and we got to replace this n with n plus 1, so 2 to the n plus 1. And of course our a sub n is just our original function. And now we're going to divide them and take the limit. So we're going to take the limit as n approaches infinity. And we are going to have the a of n plus 1 on the top. So n plus 1 squared times 3 to the n plus 2 over 2 to the n plus 1. And then we're going to flip and multiply the bottom. So that's going to give us 2 to the n over n squared times 3 to the n plus 1. Now with this ratio test, you got to break up a lot of these exponential functions. So we're going to do that now. So we're going to keep the n plus 1 squared, and then we're going to break this up into 3 to the n times 3 squared times this 2 to the n. So can't forget about that. And then on the bottom, we need to break this 2 to the n plus 1 up. So that's going to be 2 to the n times 2 to the first times n squared times 3 to the n times 3 to the first. Oops. All right, so now we're ready to cancel a lot of stuff out. So we have 3 to the n is going to cancel with 3 to the n. 2 to the n is going to cancel with 2 to the n. And then you have 3 to the first is going to cancel with one of these 3's up here. And so that is going to leave us with 3, if I could circle this, 3 halves as our constant. And I'm going to pull that outside of the limit. 3 halves outside of the limit. And that's what you want to do for these problems. You want to pull all the constants out so that all you have left is a function, a function, I guess you could say, that has the letter n in it. So n plus 1 squared over n squared. And we take the limit as n approaches infinity. Well, on the top, we just have n squared plus some other terms. And on the bottom, you have n squared. So you have a situation where the powers are the same, 2 and 2. So you can use the coefficients 1 and 1. So the limit is 1, but don't forget you're multiplying by 3 halves. So this limit is 3 halves, which is greater than 1. So that means this is going to diverge by the ratio test. Okay, last example here in the ratio test, and we're going to just keep doing the same thing. We are going to say our a of n plus 1 is n plus 1 plus 1, so that's n plus 2 factorial. And once again, we can see that there is a factorial on the top and a exponential on the bottom here. We could, just so you know, we could also use the nth term test to prove that this diverges, because a factorial is one of the fastest growing functions. It grows even faster than an exponential. So if you take the nth term test here, you can see that the numerator is always going to be much bigger than the denominator. So the limit as n approaches infinity of a sub n, this is the quickest way to do this problem, is not equal to 0, so it diverges by the nth term test. So diverges by nth term test. However, we are studying the ratio test, so we're going to use the ratio test. All right, n plus 2 factorial over 3 to the n plus 1. And then a sub n is our original series, n plus 1 factorial over 3 to the n. So now we're going to divide them. So the limit as n approaches infinity of the division of these things. So it's going to be n plus 2 factorial over 3. I'm going to go ahead and break this up. 3 to the n times 3 to the first. And that's going to be times the flip of this one, which is 3 to the n over n plus 1 factorial. So once again, we need to rewrite this as this n plus 2 factorial, as we talked before, is just going to be the number n plus 2 times the number that came before it, n plus 1 factorial. And that's going to be times 3 to the n over 3 to the n times 3 to the first times n plus 1 factorial. All right, now that we got everything broken down, we're going to cancel. That's gone, that's gone, that's gone, that's gone. And we basically have left limit as n approaches infinity. Now we can bring the 1/3 out if you want to, and that comes from here. And so that's going to leave us with n plus 2. If you plug infinity in, you get infinity. 1/3 of infinity is still infinity. That is greater than 1, so it's going to diverge by ratio test. Now once again, always look for the quickest way to do these problems, and in this case, the nth term test would have been sufficient. All right, we have come to the end of the road as far as different types of tests that we can use to prove convergence and divergence. Sounds like a good song I grew up on. Anyway, not that you're interested in that, but this is the root test. And the root test is used often with tests, with series that are involving nth powers. So I'm trying to give you little tips so that you can discern which test to use whenever you're given a whole bunch of different series and you're not told which test to use. So when you see a series that's raised to the n power, that is normally a sign that you want to use the root test. Here's what the root test says. Very quick and easy test. It says that the series will converge if the limit as n approaches infinity of the nth root of the series is less than 1, and it will diverge if the nth root of the series is greater than 1. If it's equal to 1, the root test, similar to the ratio test, is inconclusive. You must use another test. So let's review just for a moment radicals. If you have the cube root of something, that is the same as the inside power divided by the outside power. So that's x to the 1/3. So just know that when you're taking the nth root, so let's say you have the nth root of x, that's really the same as x to the 1/n power. So you're essentially raising the series to the 1/n power, and then you are taking the limit as n approaches infinity. So let's work this out here. We see that there's some nth powers involved here, so we're going to use the root test. So we're going to say the limit as n approaches infinity of our series e to the 2n over n to the n, all of that raised to the 1/n power. Now, when we have an exponent raised to another exponent, we're supposed to multiply those. So that's going to give us e squared, because the n's are going to cancel. So let me show that. This is going to cancel right there. But then we got to raise the bottom also to 1/n. And when you do that, that's going to cancel that n right there. And so because you're multiplying these two exponents, that's going to leave you with n. And you take the limit as n approaches infinity. If you want, you can bring the e squared to the front. I'm going to do that just so you know that you can, because e is just a number. It's not a variable. It's 2.718, and so that's just a constant. So if n goes to infinity, 1/infinity is 0 times anything is 0. So 0 is less than 1, so therefore this is going to converge by root test. And then we're going to do the last example here. We see that there's an nth power involved, so we're going to take our series and we're going to raise it to the 1/n power. And we need that n right there. So let me put that in parentheses. There's an n right there. So we're going to multiply this n to the 1/n, and that is going to cancel out very nicely for us. And so that's going to leave us with the limit as n approaches infinity of 3n plus 4 over 2n. And so we see that this is going to be another situation that we've seen many, many times. The powers are the same, 1 and 1. So when the powers are the same, you can divide the coefficients. So this limit is going to go to 3/2. That is greater than 1. So this is going to diverge by the root test. And that's it. You have learned all the tests that you need in order to prove whether series converge or diverge.